This section is 7.7. It's application of vectors. A lot of this is going to be physics, so if you're taking physics already, this section should be review for you. The biggest thing with all of these is you need a correct diagram. If you don't have a correct diagram, then you're not going to be calculating things out properly. We're going to use all of our trig stuff that we've used before, our right triangle stuff, our SOHCAHTOA. We're going to use the law of sines. If you need to review that, that's section 1.5. And we're going to use the law of cosines. That's from section 1.6. You have to be able to deal with those things or you're going to have trouble with these. So if you still are having trouble with this trig, you need to make sure you come in for some extra help. So these are all word problems. So let's start with the first one. If we have a 5,000 kilogram container and it's lowered down an incline, by a cable. The inclined plane is set at an angle of elevation of 50 degrees. We want to know what weight does the cable carry and what weight does the inclined plane carry? And those two, the cable and the inclined plane, they should be normal to each other or perpendicular. So that should be the normal vector. All right, so what does that mean we have? Well, we have this plane, this inclined plane, this ramp. It's got an angle of elevation, so from horizontal up of 50 degrees. And we have this container that's sitting on it. Now, when you have weight, where does weight go? Well, your weight is going straight down into the earth. So that means that this weight of 5,000 kilograms is going straight down because that's where gravity pulls it. That's where the weight is. Now the cable is carrying it this way, and the plane is pushing up against it perpendicular to the cable. So how does that help us? Well, if we sort of rearrange these things, we'll see that the planes, how much it's carrying, plus how much the cable is carrying, obviously together they have to be carrying the whole weight, right? Now, we said before that we could move our vectors around as long as they kept the same magnitude and direction, same length and direction. So what we have here is we just took this plane and we're going, the weight it's carrying is down here. So we took the weight the plane is carrying and the weight the cable is carrying, and we just added those up. That's these two. Remember, you have to put the tail of one onto the head of the other, and that weight together should be the whole 5,000 kilograms. Now, what about this angle of 50 degrees? Well, how do we get that? Well, we know that if we have this here, then this angle has to be 50 degrees. So, since the weight and the ground has to be 90, that means this one has to be 40 degrees. We know the plane and the cable are perpendicular to each other. So we've got a 90 degrees plus 40 degrees. Well, that means this one has to be 50 because the triangle has to be 180. So we have this right triangle here. We know all the angles in it, and we can figure out what the sides are. For example, we know that the sine of 40 degrees has to be however much the plane is carrying divided by 5,000, opposite over hypotenuse. So we take the sine of 40 degrees, make sure you're in degree mode, multiply it times 5,000, and we get that the plane is carrying 3,113.94 kilograms. Now the cosine of 40 degrees is adjacent over hypotenuse, so that's the cable over the hypotenuse. Take the cosine and multiply it times 5,000, and we see that the cable is carrying 3,830.222 kilograms. Now, you may say, wait a minute, there's only 5,000 kilograms. Why are they carrying more than that? Well, they're not really. It's just that they're overlapping, which is why it makes it easier to have an inclined plane, because we know that the cable doesn't have to carry all of it, and the plane doesn't have to carry all of it, and they overlap some. So together, it makes it easier. So the biggest thing is this diagram here. Make sure you've got the diagram. The rest of it should be trig review. That shouldn't be a problem. Let's try another one. Now, one thing you need to know is what a bearing is. When you have a boat or an airplane or something like that, we often talk about its bearing. What a bearing is it's measured, it's an angle measured from north clockwise. So if we have our compass and this is north, then the bearing would be measured from here and around clockwise. And whatever that angle is, that's going to be your bearing. So let's try one where we use this. So we have two forces, and they're acting on an object that we don't know the mass is. We'll just call it M. The first force, we'll call that F1, is 50 newtons, and it acts on the object from a compass bearing of 225 degrees, while force F2 equals 80 newtons, and it acts on the object from a compass bearing of 120 degrees. So if we have this and we want to know what the resultant force is, okay, so we want to find the resultant force acting on the object plus its bearing. So we have this mass, M, and we want to, let's see if we can put in axes here. There we go. Now what we have are these two forces. So force F1 of 50 newtons is acting on the object from a compass point bearing of 225 degrees. So 225 degrees is about over here, this bearing here of 225 degrees. But it's acting from there. So it starts in that and comes in this direction. So it's 50 newtons coming from this 225 degrees. Now, the 80 Newton force is coming from 120 degrees. So that's in here somewhere. So this is 120 degrees. So that means that this 80 Newton force is coming over here. So what does that mean for these angles? Well, if this is 225, then this angle here is 225 minus 80, or 45 degrees. And for This one, if we have, this is 120 degrees here, then we know the whole thing is 180, so that means this angle here is going to be 60 degrees. So, well, how do we get this? We want to know about the resultant force. So what we have is, we have this 50 Newton force, and we want to, the resultant is the sum. So what we want to do is we want to add. So we're going to shift this one up here, so it's parallel, moving in the same direction, and it's the same length. It's this 80, let's see if I can get this sketch good here. It's an 80 Newton force that is added to it. And what we want is, how much is this resultant force? The sum of the two forces. Well, we need to be able to figure out some things here. So let's look at our angles. Well, we know that this angle here between the two is 105 degrees. So what that means is, if we continue this up here, that means this angle here has to be 105 degrees, because we had our 80 Newton force here, and so this one was 105 degrees. These are parallel lines. Shifted up, that's 105 degrees. So that means this one is 75 degrees. Well, how does that help us? Well, we know two sides and the angle between them. We can figure out the other side. That's the law of cosines. So our a squared, which is this, f1 plus f2, equals our side squared plus the other side squared minus 2 times each of those sides times the cosine of the angle between them. So we calculate this all out, take the square root. Remember, we only need the positive because we're talking about lengths. And we get that A is 82.64 newtons. So that's our resultant force. Now, if we want to know the bearing, it's a little bit more complicated, because what we have is, we have this axis that goes through the middle here, and we know that this is 45 degrees. And what we want is this angle that goes all the way around to here. Well, using our triangles, what can we calculate? Let's see here. We can calculate this angle here, let's call that alpha, using law of sines. So what does that mean? Well, we've got the sine of alpha over side across from it, 80, has to equal the sine of, well, we know the 75 degree one, over the side across from it, which we just found out was 82.64. And we multiply, take the sine of 75 degrees, divide by 82.64, multiply times 80, then take the inverse sine of that, and we get that our alpha is 69.24 degrees. So that's this angle here. But we want this one that goes from here all the way around here. Well, all the way around is 360 degrees. So if we know what this little part of alpha is and subtract it, we can subtract it from 360 and get what we need. Well, we can do that because we now have this 45 degree part here. So we subtract the 45 degrees off and we get 24.24 degrees. And then we take 360 minus that and we have our bearing of 335.76 degrees. Now you can see how the picture is just absolutely essential to get right. So that's going to be the biggest challenge, making sure you understand the physics well enough to get the pictures right. Play around with them and make sure you're thinking it through logically to get it. Make sure you go through every single example in the book carefully, and then when we do the assignment, make sure you ask any questions you have and check your pictures before you move forward in calculations, because you can do problems like this till we're blue in the face, but they're all going to be different, and if you you're still going to be able to run into one that you're not quite sure about. So make sure you get the general understanding of how to get your picture right and how to add these vectors, like we talked about in the other section, to be able to understand this.